These are practice exercises from page 94 of the textbook. We're learning how to create empirical and molecular formulas for substances based on either mass information or percent composition information. So when we think about these problems, writing empirical and molecular formulas, what we really want to think about is what a chemical formula tells us. So a chemical formula gives us the mole ratio between atoms. So that means that the entire point of doing these calculations is to create mole ratios. So no matter how they give us the information, if they give us percentages, if they give us masses, we want to figure out what the mole ratios are between the various substances. So let's take a look at this first problem here. We know that the compound contains carbon, hydrogen, and oxygen. So we have this general formula that's going to be C something, H something, O something. And I'm putting those colons in because it's a ratio. It's a ratio of carbon to hydrogen to oxygen atoms. So we need to figure out what that mole ratio is. The best way to do that is to convert all of the grams into moles. Once we know how many moles of all the substances we have, we want to find a ratio between the moles. In order to find a ratio between the moles, what we typically do is divide by the smallest number, in order to figure out what the ratios are as whole numbers. So let's start by converting our grams to moles. If I know that I've got 3.758 grams of carbon, it's pretty straightforward to convert grams of carbon into moles of carbon. You can use your periodic table to find that every 1 mole of carbon has a molecular weight of 12 grams. And doing that math will tell you that we've got 0.313 moles of carbon. We can do the same thing for hydrogen. We've got 0.316 grams of hydrogen. Again, using the periodic table, we're going to cancel out the grams, change it into moles, and every 1 mole of hydrogen is 1.0 grams. Again, remembering that we're rounding the masses on the periodic table to 1 decimal place. So you notice that this doesn't really change our number. We still have 0.316, but now we have units of moles of hydrogen, and that's what's important, because again, we want a mole ratio between these various atoms. Last one we're going to look at is the 1.251 grams of oxygen. Again, using the periodic table, we know every mole of oxygen weighs 16 grams. That's our molar mass, grams per mole. Doing this calculation, we get 0.0782 moles of oxygen. And if we look at this, we can see that the smallest number is the moles of oxygen. So we have the least number of moles of oxygen. Since it's easier to look at these ratios when they're whole numbers, we're going to go ahead and divide everything by that smallest in order to get a whole number. So we're actually going to divide this one by itself, and that gives us 1, and that makes sense because any number divided by itself is 1. Do the same thing for the hydrogen. And we're going to get 4.04, which is pretty close to 4. The only time you don't want to round is if you see something that's very obviously a quarter, 0.25, half, 0.5, a third, 0.33, 2/3, 0.66, or 3/4, 0.75. Other than that, rounding is acceptable for these. Last calculation for the carbon. And we get 4.00. So what this tells us when we look at our ratio is that the ratio of carbon to hydrogen to oxygen is 4 to 4 to 1. There are 4 moles or 4 atoms of carbon for every 4 moles or 4 atoms of hydrogen for every 1 mole or 1 atom of oxygen. So when we write this into a chemical formula, the formula becomes C4H4O. because we don't put the number 1 into our formula. Since all they wanted was an empirical formula, and an empirical formula is just the simplest whole number ratio, we are done. This is the simplest whole number ratio between these atoms. And again, the way we write chemical formulas, we want to know the mole ratio between the atoms. Anytime we have information, either grams or percent composition information, we change the grams into moles, then we divide by the smallest, so that's what we did here. We identified the smallest, we divided all of them by the smallest, so we can get whole numbers for this ratio. So if you look at the way the second problem is set up, this time they're not telling us how many grams of everything we have, they're giving us percents. Specifically, they're giving us percentages by mass or percent compositions. So looking at that information, again, we know we've got 3 atoms in here, carbon, hydrogen, and oxygen. And this time, they're giving us this extra piece of information, a molar mass. We'll talk about how to use that a little bit later. We only need the molar mass when we do molecular formulas. That's all the molar mass is good for. Okay, so how do we change something into moles when we don't have grams? In this case, what we do is we assume we have 100 grams of our substance, so in this case ethylene glycol, because if we assume 100 grams, 38.7% of 100 grams is 38.7 grams. So we know if we assume 100 grams of the whole substance, 38.7 of those grams must be carbon. Do the same assumption, that means that 9.7 of those grams must be hydrogen, and 51.6 of those grams must be oxygen. We're going to do exactly the same thing we did before. We want to change all of our grams into moles because chemical formulas tell us mole ratios between atoms. So for every 1 mole of carbon, we've got 12.0 grams, which means we've got 3.225 moles of carbon. Hydrogen, every 1 mole weighs 1 gram. Again, I know it doesn't look like this calculation changes anything numerically, but we need it to change the units so that we now have 9.7 moles of hydrogen. And lastly, for the oxygen, 1 mole of oxygen is 16.0 grams. So we're looking at 3.225 moles of oxygen. Again, we want to identify the smallest one, and in this case we have a tie for smallest. The moles of carbon and the moles of oxygen are both the smallest, so we're going to divide everything by that number. So it makes sense that we're going to get 1 for that. In this case, we're going to get 3.01, which again we can round is pretty close to 3. And again, dividing this number by itself, we're going to get 1. So this tells us that the ratio of carbon to hydrogen to oxygen is 1 to 3 to 1. So if I write that as a formula, it would be CH3O. Now this is an empirical formula because it's the simplest whole number ratio. The next part of the problem asks me for a molecular formula. We know that the molecular formula is related to the empirical formula. All the molecular formula is it's some multiple of the empirical, and is a whole number multiple. In order to figure out what the molecular formula is, we use the molar mass. So we know that the molar mass of this compound is 62.1 grams per mole. What we want to check is what is the molar mass or molecular weight of the empirical formula. So if I find the molecular weight of CH3O, that's going to be the carbon plus the 3 hydrogens plus the oxygen And that's going to give us an answer of 31 grams per mole. Well, if the empirical formula has a mass of 31 grams per mole, but the actual molecular formula, the molar mass, is 62 grams per mole, we know that it's different by a factor of 2. And the easiest way to see this is to divide the molecular weight, so molecular formula, mass, over the empirical formula, mass. So in this case, I know that the molecular formula mass is 62 grams per mole. Dividing that by the empirical formula mass of 31 grams per mole, I can see that they are different by a factor of 2. So if I multiply my empirical formula by 2, it becomes C2H6O2. So that factor of 2 tells me what to multiply my empirical formula by to get my molecular. And again, the only way to get a molecular formula is to know the molar mass. The empirical formula is what you get first. You always solve for the empirical formula first, and you can move on to the molecular only if they give you a molar mass to work from. Next way